Let's do the recording. But to be honest, I think since my screens are mirrored, right, so it doesn't really matter, but just check for me as well.
It keeps returning page unfound.
It's okay. Let's optimistically assume it's recording. And
are you screen sharing on Zoom itself right now?
On a web client, yeah. Okay, so if anything, we will lose this lecture, but hopefully we won't. Something I wanted to say, I forgot. Yeah, so I will probably set up like a YouTube live stream. It's just easier in the end, then I don't have to. I think it will then record automatically and save everything on YouTube versus first going to Zoom and then me uploading to YouTube. So in that one, you will be able to see live just because, okay, if you don't join, you just watch the stream, right? So that will be fine. But anyway, so just a couple of things before we start, just to make sure that we all are on the same page. So don't forget that you have to start reading those wonderful chapters in the books, right? So essentially after every lecture, we have, almost after every lecture, we have a tiny assignment. So last time it was this chapter 0 from the cs5460 book, and chapter 5 from the OS in 3 Easy Pieces book, right? So please read them because again, first of all, it will help you to stay on track. So I kind of started slow, but my curve will go kind of very, very steep soon and fast. So don't fall behind. So, and those chapters are, again, they're very easy right now because it's still an introduction and you don't have to really like follow a lot of things, but it will escalate fast. So the complexity will be growing. So please read them. And again, there will be a quiz by the end of the week. And hopefully we finally have our TAs. So we will start assigning homeworks, hopefully we'll assign homework 1 today. We'll start office hours as well, probably starting next week. So, but there will be a week of time to finish the homework. And the first homework will be easy itself. Again, easy for most people, but if you never tried working in command line, it will surprise you a little bit. But again, everything is explained, so it shouldn't be hard. So I did, so just to avoid a confusion. So the reason I put it there originally was because people usually ask me again, can you put the homeworks so we can see what's coming? And I did it, and but since it's next to our current date and it's not yet assigned, I took it down, but it's still there, so you can find it. So, and the same will happen for homework too. So I will remove it briefly as we approach the deadline. And like one notice, I will change them most likely. Not all of them. Some of them are very hard to change. And some of them we change once in several years. And some of them are easy to change or modify slightly. So watch out. Don't jump on them and don't work through all the homeworks right away. So just make sure that you can, but there will be slight modifications. Okay, back to the lecture, right? So our goal for today is to finish IO redirection and start Intel assembly language. And why can't I do this? Because I'm already doing this. Okay, so remember what we were doing last time. So we were talking about the operating system interfaces and essentially about the fact that these operating system interfaces, which provided by the Unix kernel, are built to support the shell. And that optional video online, I mean, again, it looks a little goofy because it's from the past. So it will look a little less goofy when you finish the class and you think, okay, yeah, those guys, they make sense, actually. But the idea is that they didn't know how to interact with the system, right? Because they had this kind of a printer which was printing back results of their commands. And they were thinking, okay, what will be this environment, right? And to a degree, they did a good job because it's still very a powerful environment, which a lot of people are using today, including me, right? And I can't say that Bash or Shell is the best language ever, right? It's a very minimal language, in fact. But in the end, it lives, and it's still a powerful thing, right? And if you use Python for your, as I was saying, I'm using it for my quick explorations, like converting text numbers to binary, doing some simple arithmetic. I prefer Python as a language versus a calculator, right? So it's just faster for me, and I can achieve like good results in Shell as well. And so what we talked about is the idea that you can redirect input and output, and so we introduced those symbols which redirect input and output, and we introduced this idea of a pipe, right? So a pipe is a mechanism which allows inter-process communication. So when I say inter-process, it means that two processes which are normally completely isolated from each other, the operating system ensures that they cannot affect each other's execution, so cannot write each other's memory, cannot block or prevent each other from taking a fair fraction of a CPU. There are attacks, obviously, right? But that's a different story, and we'll come back to it, right? But normally you cannot. But a pipe is a mechanism which allows you to connect two processes, right? So it's a buffer and a kernel, which has some limited capacity, as at 512 bytes, and two processes can essentially, typically it happens, and the only way it can happen is through a common parent, which essentially creates a pipe and then introduces them to the ends of that pipe, right? So the pipe lives inside the kernel, and each process will have their own file descriptors, which will find an entry in a file descriptor table, which will point to the same pipe in the memory of a kernel. And you can read and write into a pipe, right? And so at the level of a shell, you can construct or combine multiple commands together. So shell, which offers this command prompt, works as a common parent, right? So shell itself creates all these processes, right? So it creates cat, create grab, and create WC. So this is the three processes, right, which will be running, like there will be a shell itself, which will create a cat, which will create, like this one creates cat, grab, and WC, right? So those will be children. And remember how we do create processes. So shell first will fork itself, and it will fork itself, in this case, 3 times, right? To create this 3 children. And then inside the cat, it will execute an exec system call, which will replace the memory of the shell with a cat, with the memory of the cat binary. Same for the grab and same for the WC, right? But before doing that, before replacing itself, shell will essentially create a pipe, connect these 2 children with pipe number 1, and create another pipe and connect these 2 children with pipe number 2, right? So this is how this command line is interpreted by the shell, and this is what, in terms of processes, will be running in the operating system, right? And shell will be waiting for these children to finish, and the moment they finish, the shell says, okay, I'm done, and it will essentially output another command prompt offering the user to enter the next command for execution, right? Is that clear? Just a reminder, right? And this is where we stopped last time. Where essentially I was arguing that this is better than, a myriad of these different checkboxes, which you say, do this and this. Command line looks cleaner and provides more power, right? And literally we stopped saying, okay, if we want to achieve this, what does the operating system need? What does it need to do, like underneath, under the hood, to make sure that this works, right? And I just actually explain it. So that these 2 system calls, which I was mentioning, and again, fork and exec, are sufficient to make sure that shell, which executes this command prompt, right, can construct this pipeline. If you are in the area of programming languages, this command line actually resembles a streaming programming language, right? I don't know if you know the streaming languages. Those are imperative functional languages, but there are also streaming languages. Streaming languages are allow you to construct a data flow or like a stream of execution. So those can be execution stages, and in our case, this is just looks like this, right? But there are languages which allow you to even join here. There might be a join operator which allows you to join the result of those computations, right? And somewhat like I'm not an expert in TensorFlow, but this is kind of resembles the pipeline which you can construct in those data flow oriented languages, right? But there is a domain of streaming languages which allow you to, which has a more verbose set of those operators, as I was saying. And why would this be a meaningful idea? Like, why those languages make sense? Like, one example is TensorFlow, which I don't really know much about. Unfortunately, it's outside of my domain. But sometimes, you know, like imagine you have a sensor here, and occasionally it senses something. Maybe it senses a human like walking past, you know, past the camera, right? And it sends the information upstream. And normally those stages, they sit there dormant, right? They don't do anything, right? And only when the human or the camera suspects that maybe there is a movement, then those stages start working. And they can be working on different execution units. So that might be on the edge of the network, and these stages might be in a data center, right? And then you push. And so those network, which essentially push data when it becomes available, we're driving this paradigm of streaming programming languages, right? So it's not that far away. So there is a real live domain which still like works in this area. But okay, so as I was saying, to implement this command, what shell will do is it will first execute a fork, right? Inside the shell itself, it will get the parent ID. Because remember, this is the difference. So inside the child, the fork returns 0. Inside the parent, it returns the parent ID, right? So that's the first step for the shell. Essentially, the first, and why am I spending time here? Because you will have to build a shell yourself, right? And so if you have a command line, which is something cat, then grab with some arguments, and then WC, right? So the first thing which shell does, it implements some kind of a parser, kind of similar to a language, to say, okay, this is program number 1 separated by this operator. This is program number 2 separated by another pipe. And this is program number 3. So this is P1, P2, and P3, right? And the shell will start, okay, I will fork and I will create, for example, P1. The order might be different because it depends on implementation. Maybe you will create P3 first, right? But it doesn't matter, right? But the idea here is that the shell is still running in a parent shell, which implements the command prompt, right? And in a child, let's assume it's P1, so it's a cat, right? So it's not yet a cat, it's still a shell, right? And that gives you power. So it gives you power to essentially create a pipe. So let's talk quickly about what happens to the file descriptors after fork, right? This picture tells us, and this is correct, that file descriptors get copied. So essentially, if you have a parent and you have a child, you do a fork, and the operating system kernel uses the parent's file descriptor and copies it. It creates a new one for the child. It will be a private. So the child can operate on it. It can close this one, do something in the future, right? Because there are 2 different instances. But initially, they are identical because they are copied, right? Which means that if there was like a file descriptor 3 pointing to a file in the parent, there will be the same file descriptor 3 pointing to a file in a child. Agree? So why do you think it's done this way? Why not to create it clean in a child? Why do we have this link? If it's clean, it will be just an empty file descriptor table. Maybe we can pre-create it with like standard values 1, 0, 1, and 2 for standard input, output, and error. No, it's an interesting design choice. It's a little unusual, right? What it allows you to do, it allows you to pass, for example, if you create a pipe here in a parent, like there is a system call which allows you to create a pipe. Returns an array of two pointer. What does it return? I forgot the exact syntax, but essentially it returns you two file descriptors, which are the read and write ends of the pipe, right? And so which means if you created a pipe, there will be a pipe here, right? And if you have this property that the file descriptor is copied, both parent and a child will have a copy of this, will have access to this pipe. So essentially it allows you to connect parent and a child. There is no other way in this operating system to say, okay, you have a way to be connected to connect to processes. Only a parent can create an object like a pipe and pass it to a child. Child can open files, but it cannot open a pipe. Pipe doesn't have a name. So it's either already created and passed to the child, or there is no other way to say like open pipe number 55, right? There is no such mechanism, no name. But this allows you to connect processes, to connect to child to a parent through a pipe, through this inter-process communication mechanism. And so now in order to essentially build, let's first build IO redirection. So essentially remember those symbols. The way we build them is we use this close system call, which takes file descriptor as an argument and closes it, right? And the operating system provides the following property. That's a convention in Unix as well. You can bypass it with a more explicit mechanism, but the convention is that the next open file descriptor will have the lowest number. Meaning if you have some file descriptor table, it has 0, 1, 2, 3, and you say close 1, right? This one, which was pointing somewhere, becomes null, right? It doesn't point anywhere. After that, if you say open, or you say something like a duplicate a file descriptor, like, for example, 5. If you had something here in 5, pointing here, then this 1 will be pointing to file, just because the system will choose the lowest available file descriptor, right? Again, a little unusual, but let's see how it works. So if we want to implement something like cat redirects it, the shell wants to redirect an input for cat from a standard input to a file, right? This symbol. So what shell is doing, it says, okay, I'll fork itself, right? So shell's file descriptor 0 is connected to the standard output, which is a console, right? Sorry, the standard input, right? What? So essentially what we do and what the shell will do inside the child, it will execute this sequence. It says, okay, since I'm inside the child, and like there will be some kind of an if statements here saying, okay, am I inside the child or am I inside the parent? If you close 0, this file descriptor, which used to point to the console, and open ls.c, the system chooses the lowest available file descriptor number, and this file descriptor becomes pointing to a file, right? Do you agree with this? Okay. So essentially, shell has this power to execute a sequence of code to manipulate the file descriptor of a child. And the next thing you will do here, you will do exec executing cat, right? Because cat will essentially replace memory of this child with the memory of a cat, and the cat will be running a normal cat program which you implemented, but now the standard input will be connected to ls.c, right? Is that clear? So for that, again, we need the following convention, that exec itself will replace the memory of a process, but will leave its file table untouched, right? File descriptor table, which means that if shell does something for this future program, which will be running there, it can pre-configure the file descriptor table in a specific manner, and then essentially start running from there. So that's our like again, final diagram here. So this is the end result of implementing this command in a shell. So let's take a look at another example. So imagine you're building a shell prototype in C. So it's not really a full shell, but you just want to implement a functionality which essentially redirects standard input for a program, right? This is what you will execute, right? So you will fork. And if you're inside the child, because the return value from a fork equals to 0, you close file descriptor 0, you open ls.c file in a read-only mode, for example, because it's standard input. There is no reason to write back into the standard input. And you execute cat. You pass those arguments into the cat, and this is again a convention, like an API, which allows you to pass arguments into the program. But essentially, the way it's done, you pass an array of char pointers, and the first element of this array points to the cat, which is the name of the program itself. It's again a convention. And the second argument is 0, meaning that to identify the fact that this is the last argument. So there is only one argument in this, right? So this is a convention for how to invoke exec. So is that clear? So this is how essentially shell itself internally will have a similar sequence, which essentially which will be implemented input redirection. Agree? Disagree? Any questions about it? Okay, let's keep. And so I mentioned it a couple of times. I was asking you, like, why do we really need this couple, fork and exec, right? Why not just to have exec? Maybe we can create a version of exec in which we can pass some kind of arguments to say, please, like, this is a file descriptor table for this future process, and we want it to look like this, right? So that's one way to design this API. But they decided not to do that. And instead they said, okay, well, we'll split it and do fork and exec. So why? There's a question.
I feel like it's just like this fork, you can wait for a process to be done like in one code file.
So, like maybe this returns you a PID and you can wait on this PID, for example. All right. So you can wait on your own children and wait till returning the PID on which is finished. So like Windows went this route, right? So Windows itself doesn't have even an idea of like file descriptor table, right? So I mean, I didn't look in a while, but when I was still a student, right, there is something like a process create, which takes a bunch of arguments, but there is no this idea of fork in it. And decided they went this route, right? And someone last time actually had this idea. I forgot one of you guys. You guessed correctly. So because it turns out that ensuring full flexibility of this API is hard, because really what this combination of fork and exec allows you is that you can execute a window of code in between, and you control this window. So it can be like Turing complete. You can open any file descriptors, close some file descriptors, do whatever you want, right? And it is encoded in the language. In their case, it's C, but you can use any language because API of system calls can be accessible from any language, right? And so this allows essentially a Turing complete power to essentially say, okay, I will manipulate your file descriptor table, right? So let me just erase everything on this slice. If this is the shell, and the end goal is to create 3 processes, right? So for example, you might say, because you have something like cat, pipe, grab, pipe, WC. Like in this case, you probably can like say, okay, I first create one pipe, another pipe, and then I can, for each of these processes, I will be passing arguments of this pipe as inputs and outputs. But what you do here, you can, for example, create one child, and then this child forks itself again twice, right? And makes this connection, the pipe, and then this maybe again forks, which ends up with like this recursive construction allows you to essentially construct a full pipeline saying that this is my cat, sorry, this is my grep, and this is my WC, right? And it's all encoded, like there's no link here, right? So essentially, this allows you to essentially, this allowed them to say, like, I can do something in this window of time and manipulate the file descriptor table, connect parents and children, do whatever, redirect input output, connect to pipe, and then run the pipeline later. So it's allowed them this flexibility. So is that clear? Right. Otherwise, this API of create process would become very weird. Although people, I mean, the irony of it is that despite the fact that this construction lived happily in Unix for like 50 years, right? Today, people are actually actively looking into ways of getting rid of fork. So because implementing fork is a heavyweight operation, so it's a little weird. You have to copy the entire memory of a process. There are techniques to avoid copying the entire memory and doing the copy and write, meaning that the memory originally, and I will explain it later, points to the same page table, and then only when there is a write, then you have to split a specific page in two to make private copies, right? But nevertheless, if you're running virtual machines or like containers or library operating systems, then fork becomes problematic because you say it's a complicated API, and people said, okay, do we really need it? And if the only goal is to connect processes with pipes or do something like that, maybe it's not worth it. So there is still a research conversation about whether it's worth or not, and not clear. But this is how at least we lived for 50 years and still doing it. Okay, so let's come back to this motivating example, right? So we were essentially, the idea was to connect multiple programs together, right? So that we started it last time. And the shell does it for us. So essentially, it will attach the end of a standard output to the left side of a pipe and attach to the standard input of the program on the right side of a pipe, right? And so we understand how it works. So if I show you how this pipe API works itself and implement it in a language, and again, C, this is of a piece of code which allows you to implement something like WC reads on the end of the pipe. So you first create a pipe itself. It's a system call again. You pass, I was saying, I forgot the semantics, but essentially, since in C you cannot return arrays, you can only return, you can return pointers, but this is a slightly cleaner API to say, I have an array already, and it passes inside, and it will, if this array originally has two values and which are undefined, by the time we return from pipe, this will be two file descriptors, maybe 3 and 4, which point to the read and write end of the pipe. Question? Yeah. A couple of slides. So what happens here? So again, you fork because your goal is to implement something like pipe WC, right? And so you, this program, which is main, for example, will be running on this end of the pipe and will be writing into this end of the pipe. So you fork inside the child, you say, I will close the file descriptor 0 because it's a standard input for WC, right? There's another system code which says duplicate. So remember that this array, which you got here, has two ends of the pipe. The read end of the pipe is this, and this is the write end of the pipe, right? So you say, I will since I close the file descriptor 0, my file descriptor 0 points to nothing now, right? But you have this, let's imagine you have 3, which points to the read end of the pipe. Do you agree with that? Now you're duplicating this read end of the pipe, which means that this connection is created. And so you're inside the child, which you created, this file descriptor 0 points to the read end of the pipe. And this is the convention that this is the read end of the pipe, this is the write end of the pipe. This is just an API specification which says, okay, this is how we will return these two values, right? And then you say, okay, and I will actually close both. I will close both read, so this 3, and I will close 4, which was pointing to the right end of the pipe, to make sure that those entries are empty, right? And then I will execute replacing memory of a child with the WC, right? And WC will be running there in the child, waiting for the input. And inside the parent, what I will do, I will say, since I have the right end of the pipe, which was returned in this P as file descriptor 4, I will write hello world. And at this point, I used again the same write system call, which I would be using for writing files. So it's the same idea that this is a pointer to a buffer, and this buffer is allocated in a static, or it's a global variable essentially, right? But you still have to pass a size because it's the API. And then you close both ends of the pipe, and then you can exit, right? And WC will exit as well, right? Why? Because since we were careful here, remember how WC is implemented similar to cat, and cat loop was an infinite loop, which was waiting for the pipe to be closed, meaning that normally you say you can read 0, which means the pipe is empty, but in the future someone might write something into that pipe, right? So you keep looping. But if the pipe is closed, essentially all read ends of the pipe are closed. And this is a little bit tricky because those all write ends of the pipe. Right ends of the pipe exist in both programs, in a parent and a child, right? So you have to close them all. Otherwise, it might be that the program itself writes into a pipe, right? But if all write ends of the pipe is closed and the pipe is empty, at this point, your infinite loop exits and WC will say, okay, I counted everything. There will be no other input on this standard input for me, right? And at this point, WC exits, and you will exit here from the parent as well, saying that I'm done running. Yeah.
I don't understand why you have to close the pipe in both processes.
Because let me just clear everything. Imagine the pipe is implemented by the operating system, right? It counts how many, let's assume that those are the write ends, right? And those are the read ends. And imagine I on purpose, like, let's count how many ends we created. Okay, let's start it from the beginning. So count step by step. So when we created a pipe inside the parent at this line number 3, there were like 2 pointers to the pipe, and the operating system counts those pointers like reference counts. And you will see the implementation later, x86 implementation. So 2 ends. Then you duplicate one end, which is the read end of a pipe, right? This is write, and this is read. So imagine this is a parent, this is a parent, and this is a child, right? This is the case right now. And if you don't do this too, right? If you don't close, confuse myself. So this creates like, let's time point 1 creates read and write end of the pipe inside the parent itself, right? Then we duplicate a read end of the pipe, this point 2, right? If we don't close this and this, they will stay active, right? Then we, inside the child, since when we did this fork inside the child, we still have pardon. Man, I cannot.
Process have or should the child process have the read and write, but it, like the child parents exist.
Right, but I wanted to animate it properly, and I somehow get. Let's start over again. Let's actually let me change the slide slightly so we don't have to. We have a little bit of free space here. Okay, let's do it again. Let's just count it for everyone. I mean, I understand how it works, but okay, pipe itself lives in a kernel. It will have two ends. So parent, let's say created at line 3, and parent at line 3, read end of the pipe, right? So this is right. Oh, sorry. And this is, they go back. And this is the read end of the pipe, right? When we do a fork, since those file descriptors are there, they got duplicated, right? So this is a child at line 4, and this is a child at line 4 as well. Agree? So this line 4, since you did fork, duplicated those ends, right? So now you're doing line 6. So essentially duplicating the read end of the pipe in a child, right? So you do something like this, right? So if you, these two, let me just change the color here to blue. These two lines inside the parent, oh, sorry, inside the child, they close this one and this one, right? And these two lines inside the parent, oh my gosh, not this one. I have to erase again. Not erase, I will use white. So closes, since it's inside the child, go back to blue. Blue. No, still red, why red? So it closes read and write ends of the child, right? If you don't do this, then this end exists, right? So the parent itself, even if the parent finishes and it closes, but again, let's use green. Closes these two, right? Even if you don't close this blue here, the child, which will be in an infinite loop trying to read from this end, might expect that something, the kernel itself will never return an error. It will be just returning 0. You say read 55 bytes. Kernel says the pipe is empty, but there is still a write end open. So it will assume that in the future, someone might potentially write into a pipe, and it will, instead of saying, okay, the pipe will never be written again, so stop reading, it will essentially just continue returning 0, right? Instead of like -1, for example, saying the pipe is closed. Is that clear for the previous question? Okay, yours.
Why don't they have write itself enable that capability and have it called after? Because write already has the knowledge that it's got its length.
No, okay, this is a great question, and I was asked that before. In many cases, you don't have a knowledge of how much you read or write. Let me just illustrate you with an example. So imagine you use this command. You don't really know the size of this ls.c. In that specific example where we write hello world, right? Even the reader WC doesn't know the lengths. It's only you can say, okay, the pipe itself might pass this information to the read end, right? But remember this case where you say, imagine this cat ls is 1 megabyte long. The pipe itself is a limited capacity. It can only store 512 bytes. So the cat, which runs an infinite loop, will be writing some amount of bytes. Let's imagine in the first write, it writes 512 bytes. And these three programs, they run as three independent processes, right? P1, P2, and P3. Oh, sorry, this is 3. And there is a shell itself running somewhere over here. The operating system, remember my fairness example. It will give those processes torrents on the CPU. It can happen that this process will not even run first. Maybe P3 will run first. WC will try to read something from a pipe. Remember, it's still empty. It will exit, says, okay, there is nothing, no bytes in this pipe. But since it's again implements an infinite loop, waiting for some, it does a read operation, and read returns some negative result saying that the pipe is closed. So it will try again later. Maybe it will try multiple times, but then the operating system will receive a timer interrupt, or specifically when you enter the read system call and something is empty, often there will be a yield system call which says, okay, I don't have anything to do because I'm waiting for input, but there's nothing. And so the reading system might choose to run number 2, P2, will run it. This says, okay, there's nothing on my input either, so I yield. Then this guy runs P3. It writes 512 bytes into the pipe. Maybe the shell runs then. Shell says, okay, I'm waiting for those guys to finish. I have nothing to do. Maybe P2 runs because it's not deterministic, and most likely in x86 it's a round robin strategy. So most likely P3 will run again. At this point, P3 says, okay, what's on my input? Again, empty, because this pipe is still empty, right? And then P2 runs again. P2 says, okay, I see 512 bytes, but maybe I'm reading only 64 byte chunks, right? And it reads 64 bytes from a pipe and essentially writes maybe 64 bytes into this pipe, right? And then it goes on and on and on. But often, like if you want to pass 1 megabyte, this picture will continue for a while. They will be taking turns trying to push data into a pipe. And only when this guy says, okay, I read the whole file, ls.c, I reached the end, right? At this point, it says, I'll close my end of the pipe, my right end of the pipe, saying that, okay, well, there will be no more data written into it. And then when this guy picks up all the data, maybe it will take a couple of turns if it reads in chunks of 64. But when it reaches the end, it says, okay, I got it, it's empty. It will also close its own right end of the pipe, right? So that's how it works essentially underneath. Any other questions? Multiple processes can write into the same pipe. And if you change the logic of this program, you can actually, you don't have to fork here. You can say, wow, I'm so tricky, I know what I'm doing. I will be writing into this pipe and reading into this pipe. In most cases, it doesn't make sense, but still.
So when you call the build syscall, it returns 0, right?
It returns, great question. I don't remember what it returns. I think it returns an error code because sometimes it cannot dupe. And I think if it returns 0, it means that it duped correctly.
But I look up in Google, it says it will return the new file description.
Okay, let's quickly, again, everything what I'm doing in this class is relevant to x86, right? Let's do a detour, and I'll do, I would say this one, although I'm not sure if this one has dupe. File dupe. Grab this dope with -r, just grabbing through the entire x86 source code to understand what this system call returns. So this is an implementation of the dupe system call in x86, right?
If we return that, or if we succeed, it will return the file descriptor.
Yeah, it does return a file descriptor. You're correct. But which one? So what it, just to explain the source code, this is a system call which implements dupe. It says, okay, I'm reading one argument, which is a file descriptor. And it says I will allocate a new file descriptor. And return it. So what you're saying is my code is incorrect. So No, my code is correct because I just don't care. I already know the number.
Yeah.
So apparently here it returns a file descriptor. But since I'm saying I know that my lowest number is 0, I just don't care to check. Although it's a little bit lousy, right? And it can also return a -1 saying that either I failed to read the argument correctly, this file descriptor which was passed to me, it just doesn't make sense, or I failed to allocate a file descriptor saying that there is no more capacity to allocate a file descriptor, so that's why it's -1. So ideally, my code should check for the error, but I don't.
And so now when you call execute, then you are replacing the standard in with the pipe.
When I do what?
When you execute WC, is standard input is from the pipe.
Correct. Just because we said let's again animate it here. So at this point, like if this is my file descriptor table, I have 0 pointing to console, 1 pointing to console, and 2 pointing to console, right? When I do pipe, I get 3 and 4, which point to the pipe and to the different ends of the pipe, right? When I do close 0, I break this relationship. When I dupe, and I dupe what, 3, right? Standard input, then standard, then 3, then 0 becomes pointing to a pipe, right? Correct? Okay, that was the question.
Yeah, I just want to clarify.
Okay, so is it clear for everyone?
So in source code you mentioned, why does the sysgroup argument void?
It's a convention for how the arguments are passed to system calls. They are passed. We will get to it, but apparently, like, if this is the user memory and this is the kernel memory, when you invoke let's assume this dupe system call, this P0 is on a stack inside user memory. So the kernel memory and the kernel stack on which you're running, and it will become clear when we get to this later in the class, has no knowledge of this entry. And there is this specific function call, which in the source code was something like get argfd reads value from user memory. Because those two different stacks, it will become clear later. Anything else? So all system calls are void arguments. Yeah.
So why don't we have to close file descriptor 0 in the child process?
Why don't
That point to the pipe also.
this one?
Where that in there?
This one. Why don't we have to close?
0.
So this is our read end of the pipe, right? So our goal is to close read right hand of the pipe correctly, right? And we have one right hand, so that's why we close it here. Why don't we close all other file descriptors? The operating system knows how to garbage collect them, essentially. Is that the question?
Well, we're closing P0, but isn't file descriptor 0, which is created on line 6, point to the same thing?
So let me just erase everything. So imagine this is a file descriptor table of a child, right? In the end, this will be 0 pointing to the, let's 0 pointing to the read end of the pipe, right? 1 and 2 are pointing to the console, right? We had 3 and 4 pointing. 3 was pointing here, and let's assume 4 was pointing here, right? And we are closing these 2, right? Right, because we want to let the WC running with the following file descriptor table, right? So this standard input points here, this is 0, And these two guys are still pointing to the console, right? So what are you suggesting to close? We close these two, 3 and 4, right? Because we don't want them.
So the 0, 1, and 2 after that exec runs will automatically like leave them. You don't need to.
No, exec doesn't change them, right? So that's important. So they stay. So this 0, 1, and 2, they stay the same here. They agree with this? But you're running correctly. You have standard input pointing to a pipe and standard output and error pointing to a console. And when you, inside WC, when you start running WC, at some point you will call exit. And the operating system will clean up those, saying that, okay, like all the open file descriptor will be closed and the files will be closed if no one else tries to read them. Good. Any other questions about pipes?
I just want to make sure about the deep already and then 0 on 0 on.
Oh, say this again.
Deep function, the line 3, returning no 0.
It does return a 0, as we just explored. So it says, okay, it says I duplicate it into 0, but we don't care about it because we know that it's already 0. I mean, it's a bad programming style because it might return -1, right? So, but they make the example concise to fit it on one screen. It just doesn't check for error codes, right? And sometimes you don't. If you don't do this and you say dup, then it will return 5 or maybe 6 or maybe 7, and sometimes you don't know, and that's why sometimes you will read it. It will return the lowest, right? But imagine you opened and closed files, meaning like you're running for an hour. You open some files, or like close some files, and then you don't really know which one is open, right? Unless you keep track. Good.
It will return that number.
It returns this number to the what?
I mean, the deep will return the number
Of the file descriptor, of the new file descriptor in which the old file descriptor was duplicated.
Yeah, so maybe we don't know, but after the deep return, I think we can know it's the same.
It can always return this number, right?
Always return 0.
No, it will return the number. So it's, if it duplicates 0 into 5, it will return 5 here, right?
Yeah, okay.
Let's take it offline. I can talk to you a little bit. Okay, enough file descriptors. Everyone is already, okay, so this slide was to illustrate how everything is running 3 processes. Okay, so let's try to finish here. So this is essentially this was their design vision. So they said, okay, this combination of a fork, exec, and pipes will allow us to construct complex, programs out of simple tools like this WC, grep, stuff like that, right? And that's not bad. So it still lives. And as I was saying, like we do this now in a cloud because you say, well, we'll be creating virtual machines on demand. We'll be connecting inputs and outputs of those virtual machines. There is this new paradigm, which is called serverless, right? And if you look at serverless, it's essentially just, it creates a lightweight VM without a state, but essentially pipes input and outputs to other serverless functions, which are implemented as VMs, and essentially does the very same trick with similar to those pipes, but okay, pipes have their limitations and they use the full power of whatever API and probably using Python to reconnect inputs and outputs, right? But this is how we run today. So, and they guessed this idea 50 years ago, right? And this kind of system calls, they form the core of the Unix interface. So that's why it's a little bit unusual. This fork exec combination, when you first look at it, you cannot even understand why it's done, but really it's done to connect the programs, right, with pipes. Let me quickly go through the rest of the system calls to make sure that we understand what is there. So I mentioned a couple of times exit. It terminates the current process, essentially says it never returns into a program, and the operating system terminates the process at this point. Wait allows you to wait on your child, right? So you can only wait on your children, and it returns the PID of a child which exited. So we know that we have to manipulate files, right? So we've seen open before, which creates a file. mkdir, make a directory, creates a directory in a file system. There's a unusual system call, which is called mknode, which creates an empty file, but it's backed up as a device. So essentially, it's a special file type, which says I'm a device, I can do read and write, but really it's not going in a file system, but goes to whatever backs me up. And typically it's a console in x86, but you can figure out that it can be a disk or something like that. x86 has a disk as well. fstat, file statistics, retrieves information about a file. You can, in a file system, right? So when you create files, the same file can have different names, right? And it allows you to link files, to essentially link name to a file. So link allows you to create a link in a file system, and unlink allows you to essentially delete a file. So here, what we do is we create a temporary file saying that I open a file, so it's created in a file system, but you immediately say, I would like to unlink it from the directory structure, which means the file is still alive because you still have a file descriptor, but there is no name in a file system which points to this file. And by virtue of reference counting, the operating system will know that the moment you close this file descriptor, or the moment you exit and the operating system will close it for you, this file can be deleted from a file system. It's, again, a little bit unusual, but just so you're not surprised. And the beauty of x86 and the power of this construction is that all the system calls fit on one slide, right? You know, modern operating system maybe have like 150 system calls. There are some different extensions. Not everything is a file anymore. But the beauty of x86, which we cover in this class, is that you really like just look at this page and you say, I know what's going on. So we looked at most of them: fork, exit, wait, kill. Kill allows you to terminate a process with a specific process ID. And normally there will be some access control. You can only kill so much unless you're a privileged user. But in x86, you can kill anything. Get PID allows you to, returns the ID of a current process. Sleep allows the process to wait for n clock ticks. Typically, you would be able to sleep for some number of like milliseconds and stuff, but here in x86, we just sleep for the timer ticks, which probably are 10 milliseconds. Exec creates a new program. SBRK is kind of important because it allows you to grow the process memory. And normally the process starts with no heap allocated, but SBRK allows you to grow the heap, and then you can build a memory allocator on top of that kind of chunk of space, and we will talk about it later. And you can deallocate memory by providing negative values here. You can open a file, you can read a file, you can write a file, you can close a file descriptor, you can duplicate a file descriptor, you can create a pipe, you can change the current directory, which is typically if you just do cat, then like you say, for example, exec cat, the operating system will look in your current directory. And when the process is created, it will be assigned a current directory, right? But if the cat is somewhere else, you really have to do something like maybe bin and then cat, right? Because the operating system will then search this full path, and this is a magic symbol saying that this is the root of the file system. And we have to start searching recursively into bin and then find cat there. But you can also change directory. You can change it into bin, and then you can execute cat. And I mean, again, how often do you use it? Maybe not so often, but still it's there. Make directory creates a new directory. Make a node creates a new device file. We'll take a look later how it works. fstat we covered. Link creates another name, f2 for the file of f1, and unlink removes a file. And surprisingly, this collection of system calls is sufficient to run many applications which you use today. So the only thing which is arguably missing is system calls, which allows you to connect to the network. So the network cannot easily be represented as a file, and typically there is like a connection, like an idea of a socket which you open, bind, listens, stuff like that, right? So, but besides the network, this is sufficient to run any non-graphical program which you can think of. And another powerful conclusion about x86 is that, as I was saying multiple times, in many ways, x86 resembles the operating systems which you are using today, right? So essentially, if you look at this family tree of Unix operating systems, so x86, Unix version 6, do we see version 6 here somewhere? So let's say somewhere here probably, right? Right, it was created by Bell Labs, Ken Thompson and Dennis Rich. Remember those two guys which were standing. So another popular tree of operating systems is FreeBSD, which was forked from Unix into the Berkeley software distribution, which stands for BSD, right? And then later people took and make sure that it's freely available. So essentially rewrote parts of it, which allowed us to essentially using it without a license from BSD, right? So that's why it's a free BSD. An interesting connection that your favorite macOS is sitting somewhere here, and it's a fork from BSD into Next Step. And there is kind of like cross-pollination here that really that macOS uses FreeBSD kernel underneath. So if you carefully look at it, so it uses a microkernel, which called a Mac microkernel, and the FreeBSD on top of the microkernel, and then on top of these two, they run their graphical user interface, right? So, but and this is freely available. Everything, but the graphical user interface is released as open source, just because they forked from open components, right? So they have to keep them available. Somewhere here, Linux was starting, right? So these dots are like not a direct fork, but just influence. So essentially, those ideas influenced GNU is not Unix, an attempt to change its operating system, but then Linus Torvalds started Linux as a rewrite, and now we have this as a de facto standard data center operating system today. Minix was started as a teaching operating system by Andrew Tannenbaum. You've heard of it probably. Windows was living in a DOS family, and so until Windows version 3, and then there was a Windows and Next Generation, or Next T, what? And this was using a microkernel idea similar to macOS, but they didn't have a Unix API, so it's slightly different, right? But the idea is that this x86, if you understand it, I mean, of course, x86 is what, 10,000 lines of code, source lines of code. And Linux is something like 14 to 20 millions. So it will become a little bit harder to read, but if you know the concepts, it's actually possible to get through. And I mean, it's hard for me as well, but after some break-in time, I can read. But essentially, the ideas are similar. And another interesting observation is that a lot of it actually, not a lot, but some of it was happening in Utah as well. So it's a picture from 1984, and Usenix became one of the publishing venues for those research work, for the research work in the area of operating systems. And it's still one of the two most prestigious venues, Usenix and ACM, right, which publish work in the areas of operating system, and they are hosting this conference in Salt Lake City, Utah, apparently somewhere higher up because they have snow and stuff like that, right? Because it's a summer, which is funny, right? But like people were contributing from Utah as well, so it's not that it just happened in Berkeley, and you can still talk to Mike Hibler, who actually who sits here on the third floor, who did a rewrite this fork, essentially writing a memory manager, so page tables and memory management, making sure that FreeBSD is free from Berkeley distribution. And if you search the macOS source code, you still will find his name here because they didn't delete this. So you can contribute as well, which is fun, being even a student. So That's probably the end. So at this point, I think it doesn't make sense to start assembly. We can spend these 10 minutes answering questions, or 5, or how many questions you guys have. And I will try to accelerate a little bit next time with the x86 assembly lecture. Any questions right now?
Sorry, I've seen this come up twice now. What does non-deterministic mean in this context? Because I think in the textbook it's not helpful.
Right. Okay, let me explain this. So, okay, this is actually kind of an important thing, and so people don't really understand it very well. So imagine shell creates the 3 processes: cat, process 1, grep, process 2, and WC, process 3, right? Operating system has an algorithm saying who will run first, right? And it will be accounting time. So essentially, maybe when you do this, it doesn't give you a guarantee which program will run first. Meaning that if you do it twice, maybe first time cat will run first, and second time ls or WC will run first, right? And it's called non-determinism. How it can happen? It's a great question for the exam, and I will probably ask, right? So, like, I will ask you to explain how non-deterministic execution can happen. But let me explain you. Imagine you have 2 CPUs, right? x86 booted with 2 CPUs, right? And normally the scheduler will go in order. x86 has a very simple scheduler. It's called round robin, which means that it will have an array of processes, and it will check, are you ready to run? I will run you. This runs, then it will go to the next. Are you ready to run? Not, I will skip you. Are you ready to run? Yes, I will run you. And so until it reaches the end, and then it starts from the beginning again. So which means that every process will have a chance to run, right? But because now you say, look, now this runs on 2 different CPUs. So this is still one table, but now you have 2 schedulers. And due to timing, like this might go ahead forward a little bit, this one will fall behind. In the first execution, this one gets a hold of this process and runs it. The CPU 2 will get a hold of a second process and run it. And so first P1 will run, and then P2 will run. And maybe next time you execute it, maybe this gets delayed, and this second core gets a hold of the first process and runs it, which means that P1 runs first, and then P2 runs second. Or like they run in parallel, but at slightly different speeds and stuff like that. So non-deterministic scheduling means that there is no guarantee that the processes will be running in a specific order every time you execute them, right? So that's why when you build shell, you cannot assume that the cat will run first, and then the grep will run, and then the WC runs. And we see those errors in the implementation where people assume that cat runs and finishes, and then grep runs and finishes, and then WC runs and finishes. First of all, you might not even finish, because if you're reading a megabyte in this file and your pipe capacity is 512, you can't really finish. You have to wait for someone else to read from that pipe, right? Question?
What keeps it from doing like a race condition, saying like the second process is a lot lengthier than the first 3, and the first one goes through all 3, but then like what keeps it from hitting a race condition if they both enter the next, the 4th process?
Not entirely sure I can answer the question, because okay, what's the essence of this question? So you're asking why?
How does the process keep from doing race conditions in the round?
Right. That's why I cannot answer, because what is a race condition? What do you think is a race?
Well, all 3 of the programs for the first one have already completed it, but the second one completes exactly at the same time to try to enter the 4th process together.
No, hold on. Let me first give you an example of a possible race condition here, and then maybe we'll discuss, because it will become clear. So imagine you created 3 of these guys, and imagine we just take a look at this cat P1 and grep P2, and imagine somehow they even run on 2 different CPUs, which means that they are executed in parallel. That they don't take turns. They're physically executing in parallel. And imagine this guy says write, and this guy says read at almost the same time, right? And we can say, okay, something must be happening on a pipe here, because if this one will be writing, this one will be reading, they can overlap in some weird fashion and something weird will happen, right? And we can say that this is a race condition, right? I'm slightly imprecise here because to define it more carefully, we will do it later in class, like after midterm, and you will understand like details of it. But just to give you an overview, operating system will be using, so here you did a syscall, right? Remember in my source code, it will be syswrite. So you call right here, but inside the kernel, it's syswrite. And inside the kernel here, it's sysread, right? And they will be using a synchronization primitive, a spinlock, which allows you to implement a critical section. The way it works is that only one process or thread of execution can acquire a spin lock. And when another comes and tries to acquire it, and it's a single spin lock, it has to wait, which means that one of them, oh, this is magical. Oh, yeah. One of them will acquire a spin lock and atomically will perform the whole write operation. And the second will have to wait. And the way it works, it's a little bit mysterious here or magical, is that there is a single memory here. And those guys are executing instructions on two different CPUs, right? And imagine acquiring a spin lock requires a checking of status of this memory, saying, are you already acquired or are you still not? And at the same time, writing, for example, 1 to say, I acquired it, right? And this guy here does the same. The question is, what happens to this memory? And I will answer it again in details. I mean, again, I was asked the same question last time in a hallway, so that's why I'm coming back to it. Are you familiar with the idea of cache coherence? Like, again, some people, but not enough, which is, again, you need to know it, especially people who took like 3810, computer organization, cache coherence. The idea is that the cache lines are bounced. So essentially, these two CPUs implement kind of like a network between them. And they exchange the memory in the units of cache lines, which are 64 bytes. And only one CPU at a time can essentially access the cache line. And there are some guarantees that this cache line can be pinned to that CPU for an amount of time, which means that you can do a read, do a check, and do a write back saying, I acquired the cache line. And if here the instruction, like a move instruction, which tries to access the same cache line, it will have to wait for this first operation to complete. But essentially, think of it as like a physical piece of paper on which you write how much noodles you still have left if you're trading noodles, right? And you pass it to your partner saying, okay, you sold some, let me update. But it's a single writer, multiple readers. And so we will explain it. But this is how it works. And so the synchronization is very important because imagine even like adding two elements to a linked list. Like if you try to, two CPUs try to update a pointer, one wins and you lose another pointer. But if you use synchronization primitives, it will work. And, yeah.
So say like, I guess kind of what you're saying, the lock is for the scheduling system, a spin lock will be used to avoid scheduling conflicts, right? So both scheduling the same task at the same time. There would be a lock in place there.
Kind of, but it's a little bit more general. So it's avoiding ensuring consistency of access to the same data structure. Roughly speaking, it can get as simple as a counter. Imagine you are incrementing a counter, an integer. An increment is actually two operations at the level of a CPU. Read of a memory, read of a memory, increment of a value in register, and write of a memory. If you're doing it on two CPUs, you might lose values. And again, in one of the homeworks, I will ask you to do this experiment, do the counter without synchronization, and you will be arriving to incorrect values. Just because you read on both CPUs, you read, for example, 10, you say, I will increment, but since you read 10, you don't go to 12. You say, both of them go to 11, both write 11 back, but expected result is 12, right? And if you do a spin lock, you say, look, only one of them can run atomically. One says, okay, I will do the whole sequence, read, update, and write, and it will go to 11. And the other core will say, yeah, now I can have a turn. It will go from 11 to 12. So it's at this level because you can write two things in user level, no exits, just accessing, roughly speaking, the same memory location. So user memory is not shared, but kernel memory here will be shared, so that can happen in the kernel. Let me probably stop here just because it's time. But we will come back. Okay, next time, x86 assembly. So it's a lot of fun as well.
You were talking about P1 and P2 processor, right? Like, we were sharing an example, right?
Mm-hmm.
So